Everyone, today we're going to talk about this system and then this system. Oh, the resolution is not great. Anyway, this system has this switching signal, sigma associated with it. And first of all, we have, instead of one, it's not like a typical LTI system. This is linear switch system. And instead of having only one state matrix, we have three. And we have this R2, right? And we divide the region into three parts. Not a good color. Yeah. And the rest of is like, you can imagine being green or something. So when the state is in red region, we have A1. When it is in blue region, we have A2. When it is in green region, we use A3. Basically, this is how it goes in switch systems. So also there's a I don't know, like notational or terminological distinction between switched signal or switched system and switching system. Switching system implies that switching takes place by some external signal. Here, let's say the switching takes place due to X, like due to the state, right, information. All right, so hence switch system. All right, we have A1, A2, A3, and we want to prove the stability of the system. And this system is an example system in a given in a paper that I will in the comment section you can see the details about this paper. This is a paper about the existence of convex Lyapunov functions, and then how you would go about finding a non-convex Lyapunov function and how you would parameterize those like non-convex Lyapunov functions. What are the ways that you would do that, and what are the conditions that you would impose on those parameters. Anyway, that is the material for another video, hopefully. And additionally, to specify the regions, we have three matrices. So these matrices also tell us about when we will use A1 and when we will use like A2, etc. Right? Okay. So this is the condition to use A1, right? And we have also the boundary sets, where the boundary sets are given by this definition. Okay, so we want to, the objective of this video is to show that this system doesn't, first of all, it is stable, and let's establish that. We will be establishing that, but secondly, or more importantly, although it is stable, we will not be able to find a convex Lyapunov function for this given system, and we will show why this is the case. In the previous videos in this playlist about like the convex and the non-convex Lyapunov functions, we stated a theorem and we proved that as additionally. What was the condition? Let's remember what was it. And if there exists a set, like we're just gonna look at the state space and we're gonna define a set. Of course, other than only the equilibrium point here, like we consider equilibrium point being the origin, right? And T positive, seriously positive, such that that set must be strictly included in convex hull of this set. What is this set? This notation is confinement set, and at T equals T0, you start at R0, and then starting from capital T, this set tells you the set that you are confined to, right? Okay, I mean, literally we have a video about like not only confinement set but also reachable sets. So I'm not gonna dwell on this any longer. Then yeah, if you are able to find R0 and then T such that this condition holds, then we can state that there doesn't exist a convex Lyapunov function. And then this was the thing that we proved in our previous video. And let's start, and we will show that is the case for this given system. Let's start by some definitions. Let's define some variables, simple variables. All right. So we will have z0. Okay, and you don't need to memorize this. I'm gonna show you. I'm gonna be referring back to them. So that's all right. This is the variable here. This is the point in state space. Why this point is important? Because using this point we will be defining R0 sets, okay, which is important component of our proposal. So here R0 is given by this basically, and of course these are the definitions. And then to illustrate, since this is a two-dimensional system, we will show what that is. Okay, this point is z0, and this set that I'm doing a good job of drawing is R0. Okay, so we are done with those definitions. And since this is each given system, like A1, A2, A3, they are linear, we can easily compute this, right? And then what would that signify? When you have a linear system, right? And when you, let's say, you are at x1 point in after t, capital T, where you will be is given by this expression, right? Let's say x2. Okay, so that's why this is important for us. Since these are linear systems, we can literally solve them. And solving, when we say solve, we know where it is at t1 time, and we can directly compute where it would be under these dynamics at t equals t2. All right. I mean, this is very basic stuff. I shouldn't be talking about this, but okay. So what there is not important, but our thought process is important here. All right. So this is the thing that I will be highlighting. And now we will have three more variables: T1, T2, and T3. All right. So basically, okay, this is the definition. This is the definition without saying anything about the definition. And T1 is the following: you are at Z0. Z0, and you start. Right. You start here at this location, and then you will go to that point. What is, how would you signify that point? That point is S13. Yes, this is S13. What was the other one? S21. S21. That was 32. Yeah, S32. Okay, so T1 basically is the time it takes for you to start from Z0 to reach S13. Okay, this is T1. All right, and we have T2, that is the points that it takes for you to go from this point. And by the way, we said that that point was Z1. Go from that point to, try to ignore the red line, dashed red line. It signifies something that we will be talking much later, right? Not right at the moment. ignore red line, please. Okay, just focus on the blue line here. Rather, the trajectory is given by this blue line. So just I'm not gonna like mess up this picture. This is the trajectory, right? And that is the point that you reach from Z1 to Z2. So from Z1 to Z2, the time period it takes for you to get from those 2 points is, what did we say? T2 minus T1. Okay, yeah, T2 minus T1. And so basically, T2 signifies you start from Z0 and then you end up on S32 line. Okay, and using the same set of arguments, this is Z3, and then the time it takes for you to go from Z2 to Z3 is T3 minus T2. Okay, so there's also a nice diagram. This shows what is going on here. Alright, so what did we do? We were at S21 and now again we reach S21 line. So we completed half a turn, right? Okay, and we name that point Z3. So let's check what we have so far. Z3, if you look at the norm, this is what you would get. And we define a parameter beta, and the ratio of those two norms, the point that you reached and the point that you started, is this. So immediately we can say that, oh, it decreased, like it's almost like 11%, right? Our norm, like we started somewhere, let's say this is like the norm. We start somewhere, and after some point, like after some time, it decreased, right? So this type of stuff like would give you some idea about, oh, maybe it is stable, right? It gives you hope, yeah. And hope sometimes is a good thing, right? Although it was like the last thing that came out of Pandora's box. Okay, sometimes, not always, and it's a good thing. All right. So due to the central symmetry of the dynamics, and here's the thing, this topic is something that I'm planning on making hopefully in the future. I mean, not it will not be in the past. So it's like, yeah, hopefully in the not so distant future. I will try to make a playlist about it because it's like one of those like foundational, material. So anyway, due to the central symmetry of the dynamics, which basically says that if x is the solution, so is x minus x. So it comes from basically like being odd. Like let's say we have x dot equals f of x, right? And if your dynamics, they have that property. So, and you can say that for linear systems, okay, that is always the case. Then x is the solution, so is minus x. Anyway, I mean, this is in and of itself, this information wouldn't, or this information doesn't directly give you the idea that the idea that I will be describing now. So, but keep that in mind. There are some steps that I'm skipping, and the reason I'm skipping because the subject itself is like their main point, and then there are a bunch of small points, and I would like to make a point about this like big points, right? This is the objective, and then these like small, I mean, although they are important, but they are not the objective, so I don't want to dwell on them. Okay, even to describe like what I was thinking, okay, I had to do that. All right, so after a full turn, all right, the solution reaches the set R0. Okay, at the point which is given by this beta square. All right, so we were here, we did a half a turn, and our norm decreased by beta, right? And then this says that if you do it one more time, it will again decrease by that amount. Okay, so it's basically that is the idea, like kinda, right? And we were here, -1, 1, and our norm, the ratio of the norm of this point and this point is given by this expression, right? So, okay, we understood that. And also here, this is another like interesting subject. The time it takes for you to go from this, let me get another color, this point to this point, this point to this point was t3, and then it will also be the case that the time it takes for you to go from this point, let me get another color, this point to this point is also t3, which is interesting, yeah. All right, so these are the type of analysis that we have conducted so far. And okay, what else? So now we will look at this set. So far we've been at, okay, we travel from Z0 to Z1, Z2, Z3, and then that was a half a turn, and then we continued till we reached R0, which is this line, basically compact set. And then what happened? So we switch our focus and then switch off, like, no pun intended. Okay, now we will be looking at the sets. Okay, this is the confinement set. We started at R0 and after T1, right? What was T1? T1 was the time that it takes for you to go from here to here. Okay, so basically this is the confinement set, this like blue region, right? We started here. If T1 instead of T1 we had 0, that would be, for example, I'm just gonna show you for illustration purposes, that would be the sets, right? Okay, but we have T1. All right, after this point, basically. Why? Because at that point we, like, T1, let's say, seconds has passed. All right, and okay, so now we see this R1 set, right? And R1 set is given by from origin to the point that we reached, like the point we reach after the full turn, quote unquote turn, right? Okay, one cycle. Okay, here's the thing. Wait a sec, there's a mistake. The confinement set is actually that one. Yeah, because we are yeah. Okay, now this is the confinement set. That's right. And okay, and now what we are trying to show is that the first point, R1, this R1 point or R1 set is in this confinement set given by T1 and R0. Okay, and all right, since this is the case, And of course, like convex combination of this confinement set will also include R1. Okay, we don't even need to state that. And here what was the objective? Let's check what the objective was. This is the objective. This is the convex hull. This is the convex hull, and this is the confinement set. Okay, notice we are looking at the same sets, right? R0, R0. Okay, so basically we need one set and then compact set and then a time, right? Okay, so here's the thing. Let's try for capital T, T1, and then for R, R0. Let's try if we can prove that being the case. And yeah, this is the objective. First of all, yeah, we stated that already. R1, this thing R1 is in this confinement set, which is given by this blue region. All right, we understood that. And also to show that the rest of like R1 is in, okay, let's also write that R1 is contained in R0. Okay, we want to show that R0 is contained in some sets, right? And we show that some part of it here, some part of R0 is contained. What about the other part is the main question. And to show that what we're going to do is, and here it says convex hull, right? Okay, what is convex hull? Like it's a small recap. You have a bunch of points. I mean, you might have like even points in there. Okay, got it. You have a bunch of points, and then you're gonna create other points using those points by randomly picking 2 points, xi, and xj, and then you're gonna fill out. You're gonna find all the points such that lambda times xi plus 1 minus lambda xj, right? Where lambda is in 0 and 1. Okay, if you need to do that for all I and j. Actually, that's one definition, that's an iterative definition, but another definition would be you have a bunch of points, right? I from ... m, and then you have another set which is all the y points. Let's say we are in Rn such that y is in you will have lambda I terms, where lambda I terms are all like positive or non-negative, and then some of them. So this is like a probability simplex basically. Okay, this is the definition, but let's say geometric or I don't know, like verbal definition is that you have points and then you're gonna fill out, you're gonna draw lines between the points that you have. Let's say I'm doing that, but straight line, so that was not straight, so also keep that in mind. And after you're done, okay, now you have other points, you have like infinite many points, and then you need to do that for them as well. And then after a while you will, as t goes to infinity, you will have the sets basically. Okay, I'm just filling out. I did a horrible job, by the way. Anyway, this is a convex. I think that might be the, yeah, you can clip this part of the video as like the worst definition of a convex hull. Anyway, so, all right, this is the we have this set, and then we're taking the convex hull of it. Okay, what we were trying to show is that we have the set R0 minus R1, basically the rest of the R0, right? And we want to show that this is included in the convex hull of this confined set. What was it? That was like the blue region. Here, where is it? Yeah, this blue region. Okay, so, all right, here's the thing. We will show that there exists, wait a sec. Yeah, here is the definition. We will show that there exist 2 points A and B such that they are in this set. The set that we're going to take the convex hull. Okay. Such that average of it. Okay. Or yeah, let's say average. Okay. I mean, there's like another general version of that definition, but okay, I'm going with the easy version. Okay, and so you have one set. So you have 2 points A and B, and then you have Z0, such that you draw a line, and then you see that Z0 is on that line. But this is even more convenient. You basically say that Z0 is in between those points, right? Hence, since those points A and B is in this set, of course, Z0 will be in the convex hull of the sets. This is basically what we're showing. And like numerically, A and B, for A and B, these specific values, you can show that that is the case. And hence QED, like hence, okay, for the given A and B values, you can show that Z0 satisfy, like Z0 is in between A and B points. Okay, and let's try to show that, yeah, something like that. The convex hull of the set will be like this. Makes sense? Yes, okay. So what did we do? This is the convex hull. What did we do? We were here. We were here, right? R0. And then we basically got out of some region. So I don't know how to explain this, but in a very hand-wavy way, you cannot find a convex Lyapunov function. Why? Because the system, although stable, right? This is stable. Let's establish that. And it's not like we cannot find convex Lyapunov function because we cannot find a Lyapunov function because the system is not stable. No, that's not what we're doing. The system is stable, but we cannot find a convex Lyapunov function. Why? The hand-wavy definition is that there are some systems that, I mean, again, like one more time, this is going to be like a hand-wavy definition. It will start somewhere, right? But it will do something like this. Make sense? Wait, actually, I mean, even I didn't like that hand-wave definition. Anyway, so basically, using the straight, like cold definitions, we prove that, right? I mean, there is no issue. No, not that one. Or what was it? Yeah, we proved that in our previous video. So only using the definition without even thinking about anything, and if we were able to show for a given R0 and T1, if there exists, right, those set and then T, like time period, if we were able to show the condition, then we could conclude that there does not exist a convex Lyapunov function. Okay, and here's the thing. Also, indirectly, okay, we are done with the proof now. Okay, and another thing about the stability, we basically, by analyzing the existence of convex Lyapunov function, show the stability, explain why the system is stable. Why? Because we were here, and then after one turn, we were there, right? So the norm will, again, like there needs to be like other, like facts need to be like stated and then like highlighted for this specific system, but the norm will decrease till we go to the origin. Okay, that is it. And in the next video, we will talk about how to parameterize, or one parameterization of non-convex Lyapunov functions. All right, and then what are the conditions, what are the constraints that we can impose on those parameters. Okay, here, like just to foreshadow in about what we're going to do, this dashed red line is a level set for a Lyapunov function. And if you can see that, first of all, for a convex, let's say we have this set, right, and then let's say this is convex, the level set, all the level sets would be convex, right? Yeah. If it is not convex, okay, then it is not convex as well. Like the level set is not convex, that means that the function itself is not convex. Okay, and you can see that this dashed red lines, okay, this is not a convex set, and hence, and I told you that this was a level set of a Lyapunov function that we will be analyzing, studying in the future in this playlist. And yeah, that is not convex as well, but it is used to prove the stability. And in fact, we also say that it's not like we are trying to add more function, like we are increasing our flexibility for finding Lyapunov functions, so it will be easier for us to prove the stability. It's not like that. It's not like we are doing it for to facilitate our work. We are doing this because we want to show that, we show that there are systems that are stable, and then you cannot find a convex Lyapunov function to make our job possible. What is the job itself? Is the job description is the following, and find a Lyapunov function such that, or so that, to prove stability. And now we will be looking at non-convex Lyapunov functions. Right? For those type of systems, you can only, your only hope is non-convex Lyapunov functions, because you already showed that you cannot find convex Lyapunov functions. That's it. And we will be looking at the parameterization, and impose constraints, and then again, like we do all the time, we will derive the conditions and then express the whole problem as a optimization problem, hopefully convex, right? That will be the best case scenario. Okay, that's it. And thanks for watching, and don't forget to like and subscribe.